Hello, it's Scott Manley here with a Kerbal version of a mission which is designed to unlock the secrets of the origin of the solar system. I'm launching from the old space center, you might notice as well, using Kerbal inside, which means I will launch into a high latitude orbit which will need to be corrected from, but don't worry, I have brought MechJeb along for the ride to help in a couple of places. Anyway, this is my version of the Rosetta mission. If you do not know, if you haven't heard, the Rosetta mission is a spacecraft which is visiting a comet. It's in orbit around a comet right now, and it has a little lander on it called Philae. And tomorrow, or maybe actually today, by the time you see this, it will probably have landed on the comet. Either that or it will have bounced off into space, which would be really embarrassing. But the point is, I wanted to do a version of this in Kerbal Space Program to line up with the actual mission itself. So yeah, this is Monday night and this is what I'm doing, trying to recreate this. This has a bunch of mods, obviously. We're using tweak scale to get some of the part sizes right, Ferrum Aerospace to get the correct aerodynamics. And yes, Ferrum Aerospace, because I wanted to have a spacecraft with fairings that actually did something. So there we are, this is our target. This is Comet 67P Gerasmienko. 67P means that it's the 67th periodic comet found, so I'm just going to call it 67P. I have pretty much tried to match its orbital elements to the real thing, so I've obviously scaled it to Kerbal size. First thing though is I set up a maneuver node which will take me on a flyby of Duna. Now the real mission took 10 years to get there. That's because it had to do several gravity assists. I believe it left Earth, then did a flyby of Earth, flew by Mars, and then did another flyby of Earth, and then it headed off into this highly eccentric orbit because of course its energy had been pumped up enough that it was able to get into this eccentric orbit and encounter the comet at a reasonable speed. Now Rosetta isn't the first spacecraft that the European Space Agency has sent to a comet. Back in the 80s they launched a spacecraft called Giotto, which was designed to fly by Halley's Comet. This was just a flyby, they didn't need to synchronize velocities or anything, and it actually, I think, has the record for the fastest encounter of a body in the solar system. It flew past Halley's Comet at 48 kilometers per second, and during close approach, a dust grain or a bit of dust, a pebble, I don't know, something the size of a pea, they say, hit it and knocked it off axis, and later the camera was also destroyed as part of this, but it did actually recover and they sent it off past another comet. But yeah, 48 kilometers per second, the damage done by something the size of a pea is pretty darn ridiculous. So anyway, we ditched the first stage despite having plenty of fuel left in it. And now what I want to do is make an adjustment to fly past Duna. I keep wanting to say Mars. Fly past Duna and at least make a little bit of a gravity assist. I'm not going to do like Kerbal Duna or anything like this. I just want to have a small gravity assist which will help me get into the exact orbit. And so the way this is set up, the planet Duna, or the encounter with Duna, is actually going to be pretty close to the ascending node of the comet. So the plan is, I am going to fly my spacecraft over the poles and it will kick up my inclination to be much closer to the target object. In addition, I'm going to perform a rocket burn simultaneously, which will hopefully accelerate me up to it will accelerate me up so that my semi-major axis gets much closer to the target in question. Now you can see I'm using this tool here, which is the maneuver node editor. This is actually really useful because not only does it let me adjust my relative velocity changes in tiny increments, it also lets me adjust the conics mode so that I can switch from one viewpoint to another to actually figure out where my encounter should be. So what I can do is I can zoom in on Duna and it will show me the position relative to Duna because it will be in conics mode 0. So I can see that I'm actually going to fly over the pole and therefore maximize the inclination change that I'm going to get. There's a lot of different options here, a lot of different ways I can adjust this, but I was frankly just guessing this and trying to get it relatively close to something that appeared interesting. And once I get there, I'm going to add an extra rocket burn, which will use the gravity of the planet to accelerate me even further and faster, and hopefully I won't smash into the planet. Now, interestingly, in Rosetta's case, they had a very similar maneuver where they were going to fly by Mars extremely closely, so closely that they would be in the planet's shadow for a significant amount of time. And they were concerned that the spacecraft might not survive this because the batteries really hadn't been designed for this, so they had to shut down the spacecraft. But it paid off, and they ultimately obviously have arrived at the comet. Now, Rosetta is one of those missions that's been around a long time. It originally started development in the late 80s, and in the early 90s, it was supposed to be a joint mission with the United States, but NASA ran out of money and had to cancel their half of it. So, European Space Agency built out their capabilities, and eventually they were intending to launch it in 2003, but due to a problem with Ariane, they had to delay. And that meant a switch off the target from Comet Wirtanen, which would have been a lot easier to pronounce, to Chermirov-Gersmienko. Okay, so we're flying over the pole of Duna. You can see the camera rotating around. And I'm going to initiate a burn. And what I'm mostly going to do is burn downwards to hold me in an orbit around the planet. So the idea is I'm actually going to be turning the whole orbit around by burning straight down. And this does actually give me a better use of my fuel, believe it or not, even though I'm actually firing at 90 degrees to my velocity vector. This is a very careful maneuver. We have to make sure we do not enter the atmosphere because, of course, with those giant solar panels, that might prove rather fatal for this spacecraft. You also noted that when I was doing my previous maneuvers, I had adjusted the thrust level on the rocket so I could get much better fine control. Now, I actually want to talk about the naming for Rosetta, which is actually, it's a really smart name because it's named after the Rosetta Stone, which is an archaeological artifact which was key to decoding ancient Egyptian writing, hieroglyphics. It was found, this tablet, or it was a very large stone, I believe, which contained the same text written in Latin, Greek, and hieroglyphics. And so this was the first case where you had languages which were understood in the same place as language which wasn't understood. And it turned out that a lot of the theories as to what hieroglyphics were and how they were used were completely wrong, and the Rosetta Stone fixed this. So Rosetta as a space mission is essentially a mission which is designed to help us understand ancient times in the solar system, to go back to the very start of the solar system. Comets have formed out on the very, very edge of the solar system, and they're not particularly large. So they have been in deep freeze since the start of the formation of the solar system, and because they haven't got particularly large, they haven't suffered large amounts of internal melting or transformation of the materials, so they contain relatively pristine dust and gas and other volatiles from the earliest formation of the solar system. As such, understanding comets is like the Rosetta Stone of understanding the formation of our solar system. See what they did there? And of course the lander is called Philae because that was the island on which the Rosetta Stone was actually found. Okay, so post the Duna encounter, we now need to actually pump our orbit up to roughly the same semi-major axis as the comet. Obviously, with Rosetta, they did this using multiple gravity assists. I'm just doing the one because I want this thing to be recorded in, an hour rather than 5 hours of careful manipulation of maneuver nodes. As fun as that is. So yeah, we have about 2 kilometers per second, I don't know, 2.5 maybe kilometers per second of delta V in this spacecraft. It is mostly fuel tanks, believe it or not. I wanted something that looked roughly the right shape, and I thought, well, I might as well fill it with fuel. So the performance of this spacecraft is significantly better than the actual one. But that's fine, because that extra fuel in delta V is really just compensating for my lack of patience. It turned out that this was a very, very long burn, and you can hear the music, jingling away there at 4 times regular speed, and you can see the orbit rising up. Now, unlike the real encounter, the synchronization is slightly different here, so the comet is lagging behind me, so I have to go into a higher orbit. Whereas in the real encounter, the comet is, slightly ahead in its orbit, relatively speaking, so the spacecraft ended up interior to the orbit. It makes a small amount of difference to the delta V. But now, yeah, we've got an encounter. It has an encounter of about 1,700 kilometers, which is surprisingly good considering we're going to be traveling millions and millions. Also considering that it takes a really, really long time. This is running at 12 times regular speed at 100,000 times time acceleration. This was long, tedious approach here, but once we get really close, you can see the relative velocity is starting to drop down to just under 300 meters per second. So we have enough fuel to slow us down from that speed. But as we get in close, we want to start adjusting our approach vector. So we want to look very carefully at the nav ball, and the nav ball will tell us when the velocity vector is becoming slightly offset. So we keep firing the engine to try and bring those encounter separations down. If you remember when I interviewed Felipe at a game developer conference this year, he talked about changes to the patched conics so that it would correctly calculate encounters a little better. If you remember him talking about the semi-lattice rectum, yes, we had a great deal to say about the semi-lattice rectum that day. But yeah, I'm really happy for those improvements, because in older versions of the game, before like 0.235, this encounter would just be jumping all over the place all the time. And now it became a lot more stable, which means I can make my adjustments more carefully, much earlier, and therefore save fuel, because we want to save as much fuel as possible. I don't know if I will be able to get here. Now, the real spacecraft, as it approached the comet, it performed this interesting kind of triangular orbit. What it did was it was essentially on a very slow hyperbolic trajectory, and then they would make a thruster burn, and then they would do this, and they would fly all around it. The idea being that by flying around it in various ways, they are getting an idea of the gravitational field and therefore the mass distribution. Now, it's very important that they understood the gravitational field, because this is not a spherical body. If you remember, it looks kind of like a dumbbell shape, or a rubber ducky shape, as many people like to call it. Once I got in really close, I switched over to Mechanical Jeb's navigation window, which appeared to be a little more accurate. It's telling me our closest approach was about 7.3 kilometers, and it gives me a time of 1 hour. So at this point, I start periodically firing the thrusters to slow my velocity down, because you don't want to kill off all that 200 meters per second of velocity at the last minute. No, you want to approach in a sedate and controlled manner so that you do not destroy your billion-euro spacecraft. I think this might actually be the most expensive space probe that ESA has ever flown. It seems to me that ESA is really happy to look at comets, and I like comets as well. I studied them in great detail as part of my research, and more interestingly, or more amusingly of course, had lots of interesting discussions over pints of Guinness in pubs. And it's interesting now that almost 20 years on, that some of those discussions are now going to get answers. Some of that speculation is going to get actual answers, which and I would dearly love to have more of those conversations with people in the field. It's a great thing to sit around, beer and talk about science. Anyway, at 20 kilometers now from the target object, we're orbiting more closely than Rosetta did early on. The comet in question is actually a couple of kilometers long, but even at that size, its surface gravity is less than 1 millimeter per second. So it's very weak. It's not going to hold on to a lander, which brings us to some of the more interesting features of this lander. The lander, they don't want it to fly off into space, right? So once it lands, it has 3 different things that it does to try and hold itself in position. It has a little thruster on top, which will fire. It's a cold gas thruster, which basically means that it's just like compressed nitrogen, I believe, and that will push it into the target. In each of the landing legs, it has little screws that will try and screw itself into the surface. But coolest of all, it carries not 1 but 2 space harpoons to catch a comet in space. These space harpoons will shoot out once it gets contact on the surface and hopefully go in really deep, because the thing about comets is it's expected that structurally they are very weak. They're not made of rock or solid chunks of ice. They're made of like little snowflakes, essentially. Think of it like snowflakes with dust in it, except there's a lot of dust. And those things have kind of just floated together with very low velocity encounters. So they're not like, it's not like asteroids where they have been part of a large body and they've melted and formed rocks, or they're not like icebergs in space where the ice has been stratified. They're more like snowdrifts with a lot of maybe piles of sand with lots of, moisture and snow and stuff in between them. We're really not exactly sure, although we've collected a lot of really cool data just by watching the jets of gas come off this comet as it approaches the sun. So now we've got ourselves extremely close. We're almost at 100 meters. And now what I'm going to do is adjust my orbit. We're going to travel around it because, of course, we are on the dark side and we don't want to put our lander down on the dark side. Otherwise, it will not see the light of day and therefore will not be able to perform its really important science mission. No, we need to kind of shimmy this thing around the target, so let's do that. Obviously, this doesn't have any real gravity because it's just an object. There was a mod that added gravitational objects. I'm not sure if it even works in the current version anymore, or if somebody has perhaps improved on it. I should look at these things. I've been really wanting to see if somebody that could make one that would work with dumbbell-shaped objects, but truthfully, the gravitational force from the comet is extremely low. So yeah, I just fly around it using my limited amount of fuel. And speaking of fuel, you notice that we are extremely low on our liquid fuel. I judged this almost perfectly. But we still need a little bit of fuel because the spacecraft has to drop the lander. And when I say drop, what that means is it has to kind of thrust towards the target, let it go pointed in the right direction, and then turn around and thrust the other direction. This is more or less true in the case of Philae as well, because it doesn't have any engines except for that very small, cold gas engine. So we've released it at 0.4 meters per second, which gives us a minute or so. Oh man, and it is turning immediately. Well, who cares? We're gonna neutralize the velocity of the parent spacecraft first, and then we'll switch back control to it. Now, I'm actually using the claw on it because Kerbal attachment system, the tethers and stuff apparently don't work with the asteroids. I have, however... Oh, there's the asteroid. Yeah, I've used tweak scale on this to make a very small grabber, so I'm going to arm it. Arm it? Okay, great! Apparently it's not arming. So, yes. Let's hope this doesn't happen on the real Rosetta. That would be rather unfortunate if their grabby type things broke and they bounced off the asteroid. Okay, target center of mass, and I'm going to use the thrusters at least. At least I have the thrusters. Bounce. Ah, there we go. Now let's use those thrusters, bring ourselves to a halt. No, we're kind of sliding across the asteroid. Face a little. There we have. Woo! We have landed on a comet! The Kerbal's first... Stay still! We want to make a speech about how awesome you are and how you're magnificent, you're fantastic, you are the fillet, and we won't say you're fishy. No, there we go. A first in Kerbal history, landing on this so-called comet. And there we go, yes. Of course, this is a lot bigger. The scale on this is completely wrong, but this is the largest asteroid, I believe, that comes with the game, so wasn't going to get any bigger than that. So yeah, I hope you found this interesting and educational. You should definitely follow the real Rosetta. There's a bounty of information to be discovered. But until we get more about this, I'm Scott Manley. Fly safe.